All right, you are welcome to chemistry class with Anakwe Christopher Ejike. Today we'll be looking at the topic titled chemical reactions. Our topic today is chemical reactions. It's expected that by the end of this particular class, you should be able to explain what chemical reaction is. You should be able to solve problems involving rates of chemical reactions. You should be able to state the collision theory and state factors or list factors that affect rates of chemical reactions. Then finally, we should be able to explain exothermic and endothermic reactions. We are going to be taking them one after the other, and we'll begin with what chemical reaction is, first of all. What actually is chemical reaction? A chemical reaction is the interaction of two or more chemicals to produce one or more new chemical products. When there is an interaction between two or more chemicals, it produces a new product. It could be one, it could be two, depends on the reactant. A chemical equation is used to represent a chemical reaction, whereby the reactants are written on the left-hand side and the products are written on the right-hand side, just as this. AB, react, we use plus to represent react to a compound CD to give a product AD plus CD, meaning that AB and CD are reactants. AB, we just use AB to represent a compound and another compound CD, which means that AB reacts with CD to give a product or give products AD and CD. So this is what we mean by a chemical equation, and it represents chemical reaction. All right, for instance, when hydrogen molecule interacts with oxygen molecule, they form a new product, which is water. Here we see hydrogen reacts with oxygen to produce water. Hydrogen and the oxygen here, they are reactant, and the product formed is one product, which is water. And we have it here as is being represented in the equation below. All right, chemical reaction once again is the interaction of two or more chemicals to produce one or two more products. Now, basic concepts we need to understand about this particular reaction we just talked about now is this: reactants. Reactants, whenever you hear about reactant, what does it mean? Reactants are the elements or compounds which interact with another to form new products. Those particular chemicals, those particular compounds or elements, it could be elements, it could be compound, it could be molecule that will react with each other to form new product is what we call reactant. And they are normally written at the left-hand side of a chemical equation. Now, products are the end result of the interaction between two or more elements. When two or more elements react, they will form a product. That thing that is the end of their reaction is what we call product. Now, what is now reaction time? Reaction time is the length of time taken for a reaction to take place. We call it reaction time. Some reactions are fast, some take time longer than each other. And that is what we mean. Now, another one we need to understand is reaction rates. Reaction rate has to do with the rate of chemical reaction. The rate of the chemical reaction is the rate of formation of products or the rate of disappearance of reactants. The time that it takes for a reactant to get disappeared in order to form a product is what we call reaction rate. It is the speed at which reactants are used up or the speed at which products are formed. It's also known as the rate of change in the concentration of the reactant per unit time at a particular temperature. Mathematically, it can be written this way. The rate of reaction can mean change in concentration of reactant or products over the time taken for that particular change in minutes. The change in concentration of the reactant or product all over the time taken for such particular change to happen. Or we can take it as a mass of reactant or product in mole per dm cube all over the time also. Or volume of reactant or product mole per dm cube all over time taken. All of them, time is in minutes. So this could be, any of them could be the definition for rate of reaction. It's all about the time taken for a reactant to be used up or time taken for a product to be formed all over. Has to do with time. So the change all over time is what we mean by rate of reaction or chemical reaction. All right, we are going to take a look at few questions that involves rate of chemical reaction. Let's see how it's being solved. A question like this: when 0.5 gram of potassium triazocarbonate, when 0.5 gram of calcium tetraazocarbonate 4 was added to excess dilute hydrochloric acid, carbon 4 oxide was evolved. The entire reaction took 5 minutes. What was the rate of the reaction? You see, the mass of the sodium carbonate was given to you, and the time the entire reaction took place was given. We are asked to find the rate of chemical reaction. Just bring out your equation for the reaction and you substitute. 0.5 gram, time is 5 minutes. And when you divide, you're going to have 0.1 gram per minute. That is the rate that is being given to you, gram per minute. It means that 0.5 gram of calcium triazocarbonate 4 was converted to product in 1 minute. In 1 minute, that is what it means. 0.1 gram of calcium carbonate was converted to the product in 1 minute. That is the implication of what it means. All right, another sample or another question we can look into is when a dilute solution of hydrogen peroxide was heated, the total volume of oxygen collected was 220 cm cube. In just 15 minutes, what was the rate of formation of that oxygen, of the oxygen? Now we have to look at it, volume of the product, oxygen 120, time taken is 15 minutes. Using the same formula, volume of the reactant or product all over time, you substitute, you are going to have 8 cm per minute. Per minute. Volume was given to you, minutes was given, substitute. It could be volume, it could be mass all over time taken, it could be volume all over time taken, depends on what is being given to you. It's very simple, and with that we have 8 cm cube per minute. What is non-collision theory? What is collision theory? Collision theory states that the particles of reactant must collide with a minimum amount of energy to form products. For a product to be formed, collision theory says that those reactant particles must collide with a minimum amount of energy to form products. It can't just form. There is a minimum amount of energy that is needed for that, for a product to be formed. So the collision theory assumes that there must be collisions between reactant particles for a chemical reaction to occur. There must be collision. There must be collision between the reactant particles if actually that reaction, chemical reaction will take place. That is what collision theory says, stated by Arrhenius. All right, for a chemical reaction to occur, the colliding reactant particles must possess a minimum amount of energy called activation energy. The minimum amount of energy required for a reactant particle to possess in order for a chemical reaction to take place is called activation energy. In all chemical reactions, existing bonds in the reactant particles have to be broken first before new bond can be formed in order to yield product particle. So the reactant particle, the bond in between them have to be broken before formation of the new bond. And that energy required in breaking such thing is what we call activation energy. A reactant particles must possess it before you talk about issue of formation of a new product. All right, the breaking of the bond requires energy and is possible only if the reactant particles collide with sufficient energy to overcome this particular energy barrier. What is that energy barrier? Is still activation energy. If the energy of the colliding reactant is less than that of the activation energy, they will merely rebound from each other and no reaction will occur. The reaction occurs if the energy of the colliding reactants particles is equal to or greater than the activation energy. That is only when it will overcome the activation energy, is bigger, equal to it, or greater than the activation energy, because it's the required minimum energy required for a particular reaction or reactant particle to possess. That is it. However, all reactants does not have the same activation energy, but a particular reaction needs a particular minimum of energy to possess, to have it before a reaction particle will get broken and form a new compound. All right, every reaction has its own energy of activation. As I said before, a reaction with low activation energy will take place spontaneously at room temperature. But a reaction with a high activation energy will only take place if energy is supplied in form of light, in form of heat, in form of electrical energy, or whichever, when catalyst is being added to it in order to lower the activation energy. So whichever one, when the activation energy is high, definitely something will be needed in order to lower the activation energy or increase the minimum energy that particular, increase the activation, the reaction, collision of that particular reactant in order to get formation of the new compound or substance or product needed. If that is the case, what are the factors that affect rates of chemical reactions? We have 7 of them. One is the nature of reactants. The nature of the reactants that are reacting affect the rate of chemical reaction. Another one is concentration of the reactants. Third one, effect of temperature. Temperature affect the rate of chemical reaction. Fourthly, surface area of the reactants. Fifth, presence of catalysts. Catalysts affect it. Effect of light or radiation. And lastly is effect of pressure in gaseous reactants. These are the 7 factors that affect the rate of chemical reaction. We will look at them one after the other. How does nature of reactant affect the rate of chemical reaction? That will be number 1. Nature of reactants. Of course, the rate of chemical reaction is determined by the chemical nature of a reactant, as different substances have different energy content. Ionic compound usually reacts more rapidly than covalent compound, which usually take more time. All right, let's take this as an example. For example, when a piece of iron is placed in a dilute hydrochloric acid, there is a slow evolution of hydrogen gas. But when a piece of zinc is placed in hydrochloric acid, there is a rapid evolution of hydrogen gas. But when a piece of gold is placed, there is no evidence of reaction at all. So the nature of the reactant, whatever that is reacting, the nature of the 2 compounds or 2 elements or 2 things that are reacting determines how the reaction will go. Now, let me show you this. Nature of reactants now, as I said before, covalent compounds do not break easily. It takes more energy to break the bond, but ionic compounds break easily. As we can see the structure, that ionic compound reacts faster than covalent compounds. That in reaction bonds, in reaction, bonds are broken and formed, but in ionic compounds, when it's being placed in water, it dissociates, it breaks faster than the covalent compounds. So that is it. Let's look at the concentration of reactants. Of course, concentration increases the rate of chemical reaction because there will be more molecules of that particular substance in the same volume. Thereby, a greater number of effective collision will take place. when the molecule of that particular substance increases because of concentration now, it will increase the collision between the molecules, thereby increase the rate of chemical reaction. Reactant particles will collide more if they are crowded in a small space, thereby increasing the frequency of collision. So high concentration increases the rate of chemical reaction, while lower concentration decreases the rate of reaction, the formation of those reactions. Then you can see when it's few, when the concentration is few, the molecule, they have few molecules and few collisions, and the rate of chemical reaction will be low. But when we have many molecules, there will be more collisions and the rate of chemical reaction will be greater. That is it. Effect of temperature. Does temperature affect chemical reactions? Yes. As the temperature of a reactant increases, of course, there is also increase in the rate of chemical reaction because reactions are faster at high temperature and low at lower temperatures. At an increased temperature, many more molecules obtain equal energy or greater than activation energy, which is the barrier, energy barrier. Activation energy is the energy barrier that must be overcome before a chemical reaction can occur. So increase in temperature increases the energy. It makes the reactant to possess more energy in order to overcome the activation energy. Now let's look at it. When we have low temperature, the energy, activation energy, you can see the activation energy is high. It's higher than when we have high temperature because the activation energy will now be easily been overcome because it's now lower than when it is high. The reactant particle will possess more energy to overcome it easier than when we have lower temperature. Now, surface area of the reactant is also very, very important, and it affects the rate of chemical reaction. How? Increase in the rate of its chemical reaction. It increases the rate of chemical reaction because the area of contact between the reactant particle is increased. When you increase the rate of the surface area, that is something like solid and powdered one. Of course, the powdered or granulated form will provide larger space, while it will be slower when the substance is in lumps. When it's just solid, is in lumps, it will have a smaller surface area in the reactant. So when there is a larger surface area, the reactant will be faster. Powdered or granulated substance reacts faster than a lump that have smaller space. So surface area of reactant affect the rate of chemical reaction. And look at it, when you have a lower surface area, you will have lower reaction. Higher surface area, grounded one or granulated, reaction will be faster in formation or breaking of bond and the formation of new products. So that is it in terms of surface area of the reactant. So it's affected. Next one should not be presence of catalyst. Catalyst is the substance that alters the rate of chemical reaction, but remains chemically unchanged at the end of the reaction. Catalyst, of course, presence of catalyst increase the rate of chemical reaction, since it will provide different reaction pathway with a lower activation energy. If catalyst is being added to a chemical reaction, it lowers the activation energy, thereby formation of new product will be faster. So presence of catalyst affects the rate of chemical reaction. Uncatalyzed reaction takes more time to form than catalyzed reaction. So presence of catalyst affects the rate of chemical reaction because it provides lower pathway for activation energy to be overcome. Take as an example, this, the line with a border line we see that without catalyst, the rate of chemical the activation energy, the energy required will be high than when it's now with catalyst. You see, it provides alternative or alternate lower pathway for a reaction particle pathway to be followed. So product gets formed faster than when it was without catalyst. So catalyst actually help it because it lowers the activation energy required for a particular reaction to occur. So catalysts affect the rate of chemical reaction. The next one is effect of light or radiation. Of course, light influences the rate of chemical reaction. Some reactions are influenced by light or radiation. Such reaction will not occur in the dark. If that is the case, something like photosynthesis in plant does not occur in the dark except when it absorbs light energy. So in that case, light is needed. Light affects the rate of chemical reaction. A reaction that wouldn't have happened in the dark will now happen when there is light. So hydrogen and chlorine will form hydrogen chloride rapidly or readily on exposure to sunlight or when some amount of radiation is absorbed. Reactions that occur in the presence of light are called photochemical reaction or photocatalytic reaction because light is needed or light is being supplied. That is it. The last one, but not the least, is effect of pressure. Of course, an increase in pressure affects the rate of chemical reaction. If one or more of the reactants or products are gases, it affects it when more or one or more of the products or reactants are gases. Effect of pressure will be there. If the pressure of a given mass of a gas is increased at constant temperature, it leads to decrease in volume, and hence there is a decrease in concentration, which is Boyle's law for us. So it affects the rate of chemical reaction also because increase in pressure lowers the volume of that particular substance, thereby an increase in concentration. So it affects it also. Now, look at it. When the volume is big, the pressure is lower. When the volume is being decreased, when it's being pressed down, when it's being pushed down, you can see lower volume, but higher pressure, more pressure, lower volume. This is Boyle's law for us. So it also affects the rate of chemical reaction in a when they are closed in a particular container, and the colliding will be more frequent on one another when the pressure is being increased. Thereby, the formation will also be faster. All right, let's now look at endothermic and the exothermic reaction. Endothermic and exothermic reaction. What is exothermic reaction? An exothermic reaction is a reaction in which heat is given off to the surrounding. In this reaction, energy is absorbed or liberated in form of heat energy. The energy of the product, P, is lower than the energy of the reactant, R, HR. Hence, the energy change for such a reaction is negative because the energy of the product is bigger than the energy of the reactant. Heat is given off to the surrounding. A type of reaction in which heat is given off to the surrounding is what we call exothermic reaction. Heat is being given off to the surrounding, while the product is less than the reactant. Then the total heat energy, heat change will not be negative. We'll have negative sign to show that the product is bigger than the reactant. That is it. Now look at it. In terms of energy profile, energy diagram, to represent exothermic reaction, please note that you see the starting place where this reaction started, reactant. You see the product line where product X is below. It goes down. It goes down. where the reactant X is higher than where the product X in terms of coming down, then the activation energy is the distance between where the reactant starts and where the activation complex X. Then the reaction pathway is also being given. The exothermic reaction is being represented this way, while the activation energy there, of course, we say is the energy barrier that must be overcome before a reaction must occur. And this energy condition must be satisfied before reaction can proceed at all. If the activation energy of a reactant is too great, substances which are expected to react together may not do so at room temperature because the particles do not possess enough energy to surmount such particular barrier. So particular energy, activation energy is energy barrier that must be satisfied before the reaction must proceed or even get completed. Now, where is it? Look at this particular reaction. This is a energy profile of an exothermic reaction, but distance between where the reactant is to where it goes below where the reactant started. You can see the arrow that indicates the activation energy. That is the energy, that distance between the starting point to the peak is what we call the activation energy. So that is it. In such cases, a supply of heat, perhaps in form of heat, may enable the reaction to proceed. In case if the activation energy, the reactant particles don't have enough energy, then heat will be supplied in order for it to overcome the energy barrier. Now we have what we call activation complex. Activation complex is just intermediate structure formed in the conversion of reactant to product. Intermediate between the breaking of bond and formation of new product, there is a complex we call activated complex. Now, activated complex is the structure at the maximum energy point along the reaction paths. The activation energy is the difference between the energy of the activated complex and the reactant. Now, activated complex is the highest peak of the energy pathway. Look at it. The activated complex, the peak of the parts of the formation. Of course, this particular graph shows activated complex, the highest peak, but it's the graph of endothermic reaction because you can see that the product is bigger, is higher than the reactant in case of where it started and where it stopped. But activated complex is the highest peak, is the peak of the reactants. Now, activation energy and catalyst. We are just trying to look at this, that catalyst can affect, it can alter activation energy. It can alter activation energy. The diagram below we want to show would illustrate that in order to allow the reaction to proceed at any measurable rate at room temperature, a catalyst has to be introduced. If the activation energy is more, is higher, or is bigger than what the reactant can easily occur at a room temperature, catalyst has to be introduced to lower the activation energy. And that is it. Look at activation energy without catalyst where it is. And when catalyst is being applied, it will lower it. And it comes down and the reaction can easily take place. It speeds up the rate of chemical reaction. How? By lowering the activation energy. And when he does that, the reaction will form easily. Now, when it's been introduced, as I said before, it will provide alternative pathway for the reaction, which will now have more lower activation energy. The reactant possesses enough energy to overcome this lower barrier, and the reaction therefore takes place at a much easier rate. In summary of what we have said so far, endothermic and exothermic reaction, exothermic energy is being given off, endothermic energy is being absorbed. In terms of energy profile, exothermic reaction, you can see that the product is lower in size in the diagram, while the profile reactant between reactant and the product, you can see the graph of the endothermic reaction. These are just the difference between two of them, and it's just a summary of what we have done. Endothermic energy is being absorbed, but in exothermic, energy is being given off. So far, for further discussion and inquiry, you can contact me with my WhatsApp line, +234 80 655 732, or you can send me email at send me email with this my email address at crystal116@gmail.com. Thank you and remain blessed. Remember to give us comment and comment or your own appraisal of what we have done. Thank you, and once again, get ready for subsequent video classes.